All right. We've been doing mostly beams. Make sure you realize there's no difference between the beams and a truss. This truss is statically indeterminate. Would have been a beautiful truss had they simply pinned the bottom and put a roller on the top. Would have sat still just fine. Sadly, they added another reaction over at C. So now we still have our three equations of statics, but we have four unknowns. We have E horizontal, we have E vertical, we have the reaction at A, and we have the reaction vertical at C. So we do the same thing with a truss as we do with a beam. Namely, we remove one of the reactions. Take your choice. I don't know. Maybe you could take off anything. You'd have to check. The most obvious one is the one out on the end of the truss where it's away from where you normally support the thing. So he takes off C vertical. Sadly, the structure deflects in the C vertical direction, or at least there's a possibility that it does. And therefore, the structure does not deform compatibly with the way it's supposed to deform. Therefore, we'll come back in and put some forces on it to make that deflection that we don't want go away. We never cared about the horizontal deflection at C, and therefore we don't care about it now. So you have an M0 diagram. Probably call it a P0 diagram. Diagram of all the forces inside of the structure due to the real loads applied to the released structure. And find all the forces inside of those members. Method of joints will tell you the force in member BC and DC. He has listed 0 and 0. That makes sense. Now this isn't a force. This is just an indicator that he thinks the deflection at C0 may be a number. I'm not really sure. I guess I wouldn't argue with him, but I'm not sure I like him suggesting that the deflection is down when he puts the unit load up and is going to, once you put the unit load up and combine this diagram with that diagram, you're assuming that the answer is it goes up. And so I'd kind of rather see it delta C0 shown up, because that's the way he assumes it's going to go when he puts this unit load on here. Then he comes in here and you can circle out this joint. 9 down is 9 up. This is 0, so some force is horizontal, so this is 0. Come in here and take out this joint, and you could go all through the structure like that. If it's a little short structure, method of joints will be fine. If you would rather, you could do method of sections. That would probably be a good section. You could solve for this force in this member by summing moments about D. You could solve for the force in this member by summing moments about A. Your choice. Anything that you find straightforward and simple to do probably is the best thing that you do. So here's the final answer for all the forces in the members due to the real loads applied. 0, 0, 9, 0, 7.5, minus 7.5, minus 4.5. And if you're wondering what his sign convention is, if this is 9 down, this is 9 up. 9 up must mean there's something pushing up on the joint, and that must be a compressive force. So he must be using compression as a minus and tension as a plus. Next thing you do is you take your released structure, your primary structure, and you put a unit load at the point in the direction that you would like to find any kind of loads. Any kind of deflections. Real deflections due to real loads, possibly deflections due to unit loads. You only get one choice. He decided that he thinks that this joint moves up. So he put that this reaction is up, and that this thing moves up, and that this moves up. Once he did that, he's stuck. So he puts a unit load on here. Again, he probably did a method of joints, plus one up, minus the force in this member down, except not all of it points down, only a piece of it points down. He's going to have to put the slope of the member on there, and he gets a tension force of 5/3. Summing forces horizontal, he gets the force in this member. Coming to this one, summing forces horizontal, he gets this member's force. Summing forces vertical here, he gets 0, that's a 0 force member. He comes down to this. He, in effect, takes that member out because it has no force in it. He has a pair of parallel members, a pair of collinear members, with somebody coming in from the side trying to say, can I push, can I push, can I push? The answer is always no. Anytime you have a pair of parallel members with only one member coming in, the force in that has to be 0. It's a 0 force member. And he goes ahead and solves for all the forces in the structure due to a unit load. So we'd call that, I don't know what we've been calling it, maybe lowercase p for a unit load at C. Then if you want to know the deflection at point C in this direction, you combine P0, PC, dx over EA, integrate across the length of the member, becomes P0, PC, what is that? P0, PC, dx, integral over EA. So that will be L once it's integrated. And so you multiply 0 times a minus 4/3 times the length of that member divided by the E of that member divided by the A of that member, and that's a little piece of your final answer. And 0 times anything is 0. 0 times 5/3 is 0. Minus 9 times 0 is 0. We're not getting much here. 0 on this one times 4/3 on this one. 7.5 on that one, and times 0 on this one. 0 on this one, and 4.5. I haven't got anything yet. Maybe there's no deflection at all. And finally, this guy here in combination with that guy there. That's the only number we have. It's the only pair of members that contributes to the deflection C0. Then, in order to find out how much reaction you have, you go ahead and just put a unit load. Please don't try and go ahead and put the whole reaction at C on there all at once. Not that you couldn't. Good morning. That would be integral of this combined with this, and that would tell you how much deflection you're going to get at C due to a unit load at C, which you will come in and multiply by the reaction at C, and you'll set this deflection equal to that deflection, or this deflection minus this deflection is equal to 0, and you'll solve for the reaction at C. It's an identical procedure to the moments on beams. The only difference is, instead of being moments on beams, it's forces in axial members. All right. See how I'm going to get that whole thing on there at one time. Let's get into something's got some meat to it. There's a 3-bay structure with a horizontal load on the side. It is statically indeterminate. Pixie number 1. How many degrees indeterminate? 3. Good first guess. Pixie number 2. 3 more. That's a good guess. That's 6 so far. Garza. 3 more is correct. It's statically indeterminate to the 9th degree. How I know that is I can get through these cells. I can go around. There's just no way you can go all the way from one point all the way around a structure and come back here and not have it statically indeterminate. So what I'm going to do is I'm going to cut where Pixie number 1 cut, and I'm going to release those 3 constraints. In other words, I'm going to release the ability for that horizontal member to hold axial force. I'm going to release its ability to hold shear, and I'm going to release its ability to take moment. So thus far, you have a structure that looks like this. And that's a pretty good start, because if I put a load here, I can tell you the moment, force times distance, force times distance, force times distance. If you were to put a horizontal force on this one, I could draw you the moment diagram, and I would put a corresponding horizontal force on that one, because there's no way you can do this unless you do that. Because if you say that's there, then that had to be caused by somebody, and the person it was caused by is this guy here. And I can multiply force times distance. I'm good to go till I get down in this piece here, and now I got problems again. And so what I'll do is I'll cut another piece out of there. Now I can put forces here and solve for answers and solve for answers. I can solve, 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 I can bring them together, I can solve. And then again I get down here to this closed cell. That's a statically determinate structure. Here it is right here. And here it is right here. They even look statically determinate. They don't look like they'll fall down because they look like diving boards where someone has put some little stick outs on it, and another diving board. Another possible, incidentally, how I saw how many degrees indeterminate it was, anytime you cut through a beam, you cut through 3 things: axial force, shear, and moment. So you released 3 constraints, 3 constraints, and 3 constraints. Here's another perfectly good statically determinate structure for purposes of analysis. There'd be some advantages to using that one instead of the first one. There'd be some disadvantages. Here's another statically determinate variant of that structure. Now, no doubt about it, the real loads are going to cause this primary structure to deform in horrible situations that you're not going to be happy with. Yes, sir?
What's the difference between the first structure you drew and the second one?
None at all. The only difference is where you cut it. Here I cut the horizontal members and I opened them up on the right end. Here I cut them on the left end. The number work would be identical on both of them. Here's another possible as long as there aren't any closed cells there that you can get all the way around in, that would be okay. I mean, it would really be a mess drawing a shear, not a shear, you don't need a shear diagram, but a moment diagram for a thing that looked like this. But it's perfectly good, because you can put any kind of loads you like anywhere on this structure right now, and you can solve for the moment at any other point. For instance, if you say, well, I don't believe you, I'd like to put a 1 right there. And I'd like you to tell me what the moment is right here. Well, all you do is you cut this piece off and you draw a free body of it, and the answer is what? 0. There's no moment on it. If you say, well, how about here? Well, that's fine. I'll cut that right there. The answer is 0. And you say, well, how about right here? Well, now then the answer is not 0. Now then the moment is 1 times this height right here. That's how much moment is at that point. Here's 1. So far I have removed 3 unknowns, 3 redundants. And I'll take off this wall and I'll take off that wall. That's 3, 6, 9. I've removed 9. What's wrong?
Does that work with this man?
I'm sorry?
It will just float. Yeah, isn't it just kind of floating?
Yeah, I'd say that any load on that would probably kill somebody. That's not a good primary structure. You say, well, we released 9 redundants. You did indeed, but you didn't have a stable structure when you finished, and therefore that would not work. Here's another one. Going to put a pin here, 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 a pin here. How many redundants have I released so far? 6 is correct, because you'll notice that the axial force and the shear are still in there. And I need 3 more. And I got to be careful it doesn't fall down. I could put 1 here. And this thing here might tend to flop over, but axial forces would come down here and then be carried down into there. And so I could put 1 right here, and that would be okay. And put 1 right there. Now, you do have to be careful, and you can easily get a structure that is statically unstable if you're not careful. Here's the most common way somebody might do it. They release 1, 2, 3, and it looks like all the pieces still hold up pretty well. But the problem is this little piece right at the corner itself, where you put the pins, it does not hold up by itself. Any moment that was applied to that joint would not have any resisting moment to pull that moment back out. And therefore, it would be unacceptable for a primary or for a real structure. Now, it's not like you're going to get off into weird things like this, but you should know there's no difference between solving this one and solving this one. So I'm going to choose this one. For my primary structure. I'm going to cut this out. I'm going to cut through there. I'm going to cut through there. And I'm going to basically turn it into 2 cantilever beams with a few sticks on it. The loading on the side is uniformly spread across the side, across the entire depth. My guess is that's kind of how it would deflect after all was said and done. These floors would move to the right. These things would like to kind of bend like a cantilever. However, because of this member here not liking to bend, it's going to have to come in, it's got to come in at a right angle, And since it doesn't like to bend, I have shown a little reverse curvature around those points. Then I take off the reactions, the unknowns, the redundants, the thing that make it statically indeterminate. And there are my choices. I flat refuse to call this point B and call this reaction in here the force at point B in the horizontal, the force at point B in the vertical, the force at point B rotational, or M. There's just too many subscripts involved. I'm simply going to tell you that by releasing this with a saw, I opened up a reaction number 1, a reaction number 2, and a reaction number 3. The directions that you see on there are arbitrary. Pick any directions you like. One thing you have to do, if you assume that someone is pushing to the right of your right-hand cantilever, the only person available to do that is this guy over here on the left. So you're going to have to let him put his feet on this horizontal beam so that he can push to the right. If he does so, his hands will be pushing back on his feet such that R1 is this pair of forces. Now that's not quite what you're used to seeing. You're used to seeing a beam and a reaction and a reaction, and when you took loose this reaction, you replaced it with a force. Maybe you called it R1. But in the real world, underneath R1 was a pin or a roller, and R1 was pushing down on the ground. Even when you really never saw it up till now, there was a matching force that had his feet pushing against something. So here will be our redundants. R1 will be the axial force in the top member. R2 will be the shear on the right-hand end of the top member. And R3 will be the moment on the right end of the top member. R4, 5, 6, R7, 8, 9. Here's your final set of equations. Well, yeah, nobody said that it would be short or easy, but that's why the dollars are big and nice. The final deflection at position number 1, the final deflection that these 2 points open up, should be none. In other words, once this guy gets through moving where he wants to move and where this guy wants to move, independently, the only thing common between them is the magnitudes of these forces are equal on both sides. This point will exactly match up with this point as shown in this diagram. This horizontal member will move to the right to here, and this vertical member will move to the right the same amount. And when you get through applying all of these forces, you'll find that this guy wants to move up and down, and this guy wants to move up and down, and when they get through both moving up and down by themselves, they'll be able to look over at his buddy and he'll say, howdy. He'll say, howdy. So, did you just get here? I said, yeah, I just got here. So, I notice you're here too. Yes, I'm here too. And the same way with the same thing with a rotation. When this guy has all the forces applied all the way down, and this guy here rolls because of all the forces, all 9 unknown forces you see, he'll end up wanting to do this with no help from anybody else. And when you put all those forces on this piece of steel and calculate where he wants to go, you'll find he wants to go just like this. And the two, you just move them together 1/millionth of an inch. You can weld them up. You have a perfect right angle. So, deflection number 1 is equal to delta 1, 0. That'll be the deflection in this direction due to the real loads. And by that I mean you'll put you'll put the loads on here, and you'll find that this guy here will move to the right 6 inches, and this guy may not move at all, and therefore you'll find that this is a problem. Delta 1, 0 turned out to be a non-zero number. And you'll look at it and you'll say, phooey. Then you'll start trying to piece it back together. R1 will cause some deflection between these 2 points. R2 will cause some deflection between these 2 points. And when you add them all up, you want the total distance between those 2 points, namely this point and this point, equal to 0. Now, if you missed all that, you don't have a prayer in this class. All right, so as you might imagine, here's what we're looking for. Katie, bar the door. You're looking for the deflection at the number 4 position due to the real loads. Here, for example, would be the deflection in the number 4 position. Let me pick another one because that's kind of the one we just discussed. Here's the deflection in the number 5 position due to the real loads. Due to the real loads, this thing's going to bend like this. And because the real loads are not applied to these members, they'll really just stick out straight. And here is your number 5 position, and that is a movement up and down. And my guess is when you work on it, you will find that is a negative some number of inches. That is the deflection in the number 4 position due to the real loads, except don't forget you also have to do this guy, because while he's moving down, this guy may be moving up. But when you put that reaction, or when you put a unit load, either one on here, this one's up, that one's down, we usually omit axial forces in these things that are primarily bending members. That means that this guy won't go up any or down any, and therefore this is what you'll get, delta 4, 0. Thank you. I don't know where it was a hangover from where we said it was going to be a 4. Thank you. Delta 5, 0. So I always like to see which way they turn. They usually always turn left.
What are those subscripts on, like 5, 1? What do they refer to?
These right here.
Well, that's only 1, 2. Oh, is that?
That's a 5.
Oh, it is.
Can try my best. You'll just have to remind me. All right. So when you're looking for delta 6, 0, here's your number 6 load, your number 6 position, your number 6 deflection. Delta 6, 0 would be this angle right here, added on to any angle that this guy causes due to the real load. Since the real loads didn't actually get over to this structure, he's just going to stay vertical. And therefore, this number right here will be delta 6, 0. All right. Here's your real load. Your real load got on this structure and bent it. These three didn't actually have any load, or I would have shown them bent to some extent, and maybe not. And there may even be a little bend in them. I don't remember how I drew them. This is your number one direction, and therefore how far the original structure, see it in its undeformed state, moved to the right is delta 1, 0. At least that's a piece of delta 1, 0. How far this guy moved to the right also, you would say delta 1, 0 minus this. In other words, it would be the difference between how far they moved. Or if this one moved to the left, then they would cross, and the deflection between the two would be delta 1, 0 plus, well, it would be like a prime. It would be some due to that and some due to that. And you'd have to add the two numbers.
Wouldn't the delta 1, 0 for just the cantilever shouldn't be the same as the other frame structure?
I don't know what you mean by the other frames.
Just the other half.
This half here?
Well, shouldn't the horizontal deflection for any point on that piece be the same as horizontal deflection for any point on that?
Well, are you saying should this number be the same as that number?
No, for the two structures.
Well, I see two structures. I see one of them has load on it, and therefore it did deflect. This,
But like in reality, because it's all.
we're not reality. We're primary. We're base. We're, what else did they call it? Released. They call it a released structure. We won't get to reality for days.
So that cantilever, it won't deflect at all?
Talking about this one right here?
Yeah.
All right, I cut this with a saw. Here's what the structure looks like. Should have brought more of these. Forget the bent part. Here's the structure, here's the structure, here's the structure, here's the structure. And I say, what the devil did you do to my structure? And the guy holds up this big saw and a big stupid smile on his face. And he says, I did something to it. I said, why did you do that? He said, I don't know, Larry told me to. He says, I was turning it into a primary structure. Okay, now here's the load. And so the load now then, and one nice thing about this is you can now calculate the moment anywhere inside of this F-looking thing. And it doesn't touch this anymore because the guy cut it open, and therefore this just stays straight.
I think you were saying before that the delta 1, 0 minus.
Well, that's an if. That, in other words, let's say, for example, that you did this one. Oh, yeah, thank you. Forgot we've got it blown up. Let's say that you did this one right here. In other words, when we talk about it, we do have to talk about the one that we did. And let's just say that you put unit load like that. And the only way to do that is let the guy put his feet on this and push down on that one. Then I would show you this guy curled up like that. And I would show you this guy curled down like that. And I would tell you that delta 1, 0 would be the sum of the two. If they both bend, I got to get both of those deflections. All right, so hopefully now you see that much of it. And I would hope I could ask you what any of these things are. If you go back and look at some of the old quizzes, you'll see this kind of stuff. First off, you're given this, so you know what the 1, 2, 3, 5, 7, 9, 11, 15 directions are. 3 is a rotation on the top piece. 5 is a shear up and down between these two members on the second beam. And I would put the real loads on there, and I'd ask you to draw me the deflected shape. Here are the deflected shapes due to the real load, and then label the deflections. Well, it's due to the real load, so they all have subscript 0 on the tail end. And this is the number 1 direction, this is the number 2 direction, and the rotation of this piece here is the number 3 direction. And 4, 5, 6, and 7, 8, 9. And that's delta sub I0, where I goes from 1 to 9. Now then, along with being able to find these numbers, you're going to have to draw me a moment diagram on the primary structure so that I can combine his moment diagram with some moment diagrams to some unit loads. Here's his moment diagram. His moment diagram is 0 right here. His moment diagram halfway up is equal to the area under the curve times a half of a floor's height times the distance from the centroid to that point. His moment here, his moment here, his moment here, his moment here, his moment here. You probably won't do that many of them. First thing you say, okay, it's a function of x squared. And so it's a parabola. So let me put some numbers on here just so there are numbers at least running around loose. I'll go back to the real structure. I'm going to tell you that this is 12 feet high, 12 feet high, 20 feet high, 16 feet across, and the load is 3 kips per foot. That means that, whoops, I knew that was going to happen. 20 feet tall, 12 feet tall, 12 feet tall, 16 feet across, 3 kips per foot. That means that due to the real loads on the primary structure, see, I can't tell you what the moments are due to the real loads on this mess. I have no idea. But I can tell you what the moment diagram looks like. On the structure when it's cut up into pieces and turned into a primary structure. What's the moment right here? If this is, what did we say, 3 kips per foot, and these heights were 12 feet, 12 feet, 20 feet. What is the moment right here? Better be able to do that. I know you can, but you're not about to volunteer until I pull you out of a hat. Lane, you got a hat, so you're not Lane? You're supposed to be Lane. Lane was counted here today because of you. Oh, bummer.
I want to draw an air to
All right, Clopton. Where's Clopton?
Right.
Oh, Clopton. Okay. How much moment is there right here?
3 times 12 times 6.
That's just that. Why didn't you tell me that a minute ago and save me all this grief? 3 times 12 times 6. 3 times 12 times 6 kip feet. And the moment right here is 3 times 24 times 12. 3 times 24 times 12 kip feet. And the moment down at the bottom is 3 times 20, 30, 40, 44 times half of 44, 22. That's how much moment there is at the bottom. And that's M0, or M due to the P loads, the real loads, 0. Okay. Now then, I would like to solve for example, delta 1, 0. In order to solve for how far this structure moves due to a unit load in the number one direction. First off, let me go back and make sure which way R1 goes. R1 was arbitrarily chosen as compression, pushing to the left, pushing to the right. I'll have to put a unit load in the number one direction. There it is. There's a unit load in the number one direction. Here's the moment diagram caused by unit load, no moment, no moment, no moment, no moment, no moment, 1 times 1, 1 times 2, 1 times 10, 1 times 12, 1 times 18, 1 times 24. On this side, 1 times nothing, 1 times 1, 1 times 2, 1 times 12, 1 times 24, 1 times 44. There's your M sub Q due to a unit load in the number one direction. That's a good reason to call it the number one direction, the number one load, the number one anything. Because if you start saying it's M sub Q at A in the horizontal direction due to something in the vertical, you just get lost. We said that was 12. 12, 20. Set across here was 16. Cooper, how much moment is there at the bottom? Davis, give him a hand. How much moment down here at the bottom?
It'll be the sum of, let's see, what's the length of that one? It's 20, 12, 12.
That's 44 tall.
44 tall times 18 divided by 2.
Well, now wait now. You're trying to give me an area here. You're probably getting ready to do some kind of volume integral stuff. It's a little too soon for that. I'm still trying to get the moment diagram so I can do volume integrals in a minute. I want to know how big is this number right here. It's a moment.
Let's see, it's going to be
Force times distance. How big is the force?
1.
That's correct. How far away from the point that I've asked you for the answer is it?
44.
And therefore the answer is?
44.
That's correct. That's how big it is. It's 44 kip feet. And you'll notice that whoever's doing this is plotting these moments on the tension side, so that when he combines this moment diagram, which pushed to the right, causing tension on the left, plotted on the tension side, when he combines this moment diagram with this moment diagram, which the force is to the left, that's an arbitrary selection of which way R1 is going to end up going. It caused tension on the right-hand side, plot on the right-hand side. You'll know that that term is a negative term. Integral m dx over EI. Now then, because the one applied to this, you had to let him put his feet on something to generate that force. This is what his feet did. Now his feet moved to the right, causing a moment diagram on the tension side of the vertical member, and it happens to also be 44. It didn't have to be. The two legs didn't even have to be the same length, but they both got a 1 on them, and they're both 44 feet tall. And therefore, there's the moment diagram due to a unit load in the number one direction. And if you want to find this number right here, delta 1, 0, you're going to have to integrate m, due to the real loads, 0, with m, due to the q loads in the number 1 direction, dx over ei. mm dx over ei. And that's what I'm going to want to do. Now then, that will get me this term. That's all I get. That is the integral of m due to the real loads times m due to the q loads in the 1 direction. There's your 0, there's your 1, dx over ei. You can write equations for those triangles, or you can use volume integrals. But I think volume integrals are always easier, but it's up to you. Now then, I need to make that problem go away. You'll find that's a real number. You'll find that the two pieces slide towards each other or go away from each other, and that's not acceptable. However, you'll find that the application of R1 will make it want to close up a little, and then when you also put R2 on it, it'll make it close up a little more.
What are those R's again?
Those are the reactions. Those are your answers. And delta 1,1 times R1 is the total amount that closes up because you put R1 on there. Delta 1,1 is how much it closes up due to 1 kip. But you get to put more than 1 kip. You get to put R1 kips on there. But space number 1 will also be closed up because you put an R2 on there, and an R3, and an R4, and an R5, and so on.
Wait, what reactions are those? Not at the supports, right?
No, they're not. Here, if you ever don't know what the R's are, you go back to the original picture.
Oh, yeah.
And you say, who messed with my structure? And you point to the guy with a saw. And when he opened it up, I came in there and said, no, this is not acceptable. No, you don't have these two pieces connected together. And so I said, I'm going to put R1 back where that piece of air now is. And I'm going to put R2, see how this R2 goes up and that R2 goes down? And I'm going to put R3 as a bending moment. And I'm going to fit those pieces back together. I won't be able to fit these two pieces back together just with R1, R2, and R3, because it turns out when you push on it with R6, R8, R8's going to distort everything up there too. And so R8 is also going to have to be selected such that it's included in fitting these two people back together. Those are your unknowns. All right, as you might imagine now, I need a whole bunch of deltas. First, this is the delta at any point due to a unit load at the number 1 position. You'll notice that I do indeed have a unit, phooey. Where's my hey guys? You will notice that I have the unit load at the number 1 position. By pushing on this left-hand frame, you move this point to the left, you move that point up, and you cause a rotation of that point. His name is delta in the number 1 position because you put a unit load in the number 1 position. He moved up, deflection in the number 2 direction because of a unit load in the number 1 direction. And a rotation, a deflection in the number 3 direction, which is a rotational direction due to a unit load in the number 1 direction. But sadly, that 1 also caused not only this thing to move to the left, it caused this other guy to move to the right.
So that unit load isn't really the same unit load that we used before?
It is. It is exactly the same.
I mean, it is, but it isn't in our
No,
calculation.
it either is or it isn't. And the answer is, it is. Now let me show you, I had one right here. It is exactly the same as the unit load. Thank you. It is exactly the same as the unit load you used in calculating how far 1 kip moves this thing up. It doesn't look the same, I understand, because here's what you saw when you put the unit load on there. You saw a 1.
But like in terms of procedure, we first use the unit load to find the delta
Yes,
of the release structure
right,
for the real loads.
right, but you had,
Now we're using another unit load to find the little small deltas, right? So we kind of put a unit load on there twice throughout this whole calculation procedure.
well, I'm not sure. The only thing I can imagine is when you say you put a unit load on there twice, are you talking about because on my new pictures, new today, you see 2 1s instead of 1 1?
No, I mean like when we were just figuring out this whole problem, the first time I would put a unit load on there and we found the delta 1 due to the real loads. So we got that number, but now we're taking that unit load and we're putting on it again. And now we're going to use it for a different purpose, right?
We always did that.
Yeah, I'm just trying to kind
Yeah, well, we always did that.
procedure.
I don't want to write on the back of something where if you start looking at it on the web, you can't find it again. So I guess I'll just throw these pages just about anywhere I can get it. When you did the more simple problems like this, you turned it into a primary structure by removing that. And you put the real loads on there, on the primary structure, and it deflected like this, and you were told there was a deflection in the number 1 direction due to the real loads, and you couldn't find it.
Yeah, we used the unit.
Well, then you had to have another picture, and the picture that you had was up or down, your choice, but whatever you pick, that's the direction the reaction you think it goes. You put a 1 on there, and it caused a deflection, which you caused the deflection at number 1, in the number 1 position, because of a unit load at the number 1 position. Okay? Now then, somewhere inside of your equations, you had an equation that said delta 1, 0 plus R1 delta 1, 1, and if there was only one unknown, then that was the end of it, was equal to 0. In order to get this, you combined this with this. You combine this moment diagram with this moment diagram. I don't have the moment diagram shown, but that's what you did. To find this guy, you combined this with itself. You combined to get this, you integrate m sub q1 and pretend it's a real load, and then you do m sub q1 and pretend it is a dummy load, dx over ei. That's exactly what we're doing now. The only thing I can see that looks different, that I don't know if it's confusing you and probably everybody else, is you only had 1, 1. The truth is you never just had 1, 1. The truth is on the ground, on this thing that you took loose, you had to tie the rope to this and tighten up the pulley to pull down 1, and you pulled up. There was another 1. It just went in the ground and it was never shown. Therefore, in this one, where you have a unit load, that we're getting ready to combine this moment diagram, and it's going to get worse. With that moment diagram, when you do that, you have to have a real moment diagram to do the real loads, and you have to have a unit load moment diagram. Now, the other term, the delta 1, geez, this guy right here is two of these.
Yeah, so that's how I was saying it's 2 unit loads that you're.
But it's always been two of them. It always has. Nothing new has happened here. Okay. All right. Here are the terms on this figure, because you're going to put a unit load on there, and you need a pot full of things that happen because of a unit load at number 1. You need the deflection in the number 1 direction due to a unit load at 1. You need a deflection in the number 2 position due to a unit load at 1. And you need this all the way down. Here those terms are. Same primary structure. Put a unit load only at this one location in the number 1 direction. Causes a deflection to the left and a deflection to the right. In other words, once you integrate all of the moments with all of the moments dx over ei, you'll get the sum of these two numbers. One of them will be due to this, and the other one will be due to this. There's your number 1, there's your number 2, and there's your rotation number 3. Number 4, number 5, number 6, number 7, number 8, and number 9. It's a mess. Yes, sir.
Okay, on your moment diagram, if you were to flip the side it's on, would you just change the sign?
Absolutely. But when you do that, you have no choice but to flip this one also.
You have to flip them both.
Okay? In other words, if you say, I'm not going to plot things on the tension side anymore, I'm going to plot them on the compression side, you have to do that for everything. Now, if instead you say, what I'd really like to differ from your analysis is I don't think R1 pushes on this member and pushes on this column. I think it really pulls. Then all of the tension sides due to the unit loads would change, but the tension side due to your real load would not change. You'll still get the same answer that I'll get. There won't be any difference in the answer. All right, here we go. Number 2. You see where the guy on the original unbent structure, the released structure, the primary structure, the one with the big old saw cuts on it, he pushed in the reaction number 2 guessed direction. Somebody guessed it's going to push up on this piece and down on that piece. You can guess any direction you want, but when you do that, your ones have to agree with that. And the other side of that coin is a lot of people say, no, I put the ones on here, and that's what set this guy's arrowhead. But I don't care who came first, the chicken or the egg, but these arrowheads here have to agree with your unit load guess arrowheads. That's got to happen. Therefore, when you push down on this member, lo and behold, you get nothing but axial force. You get no bending moment. This member does get very, very slightly shorter, PL over AE, but axial distortions in these members are usually very small and are usually ignored. You don't have to. You could add the PL over AE terms to the terms you have now. But bending so far overpowers it usually that usually just the bending stuff is considered. And here's 1 times nothing, 1 times 1, 1 times 2, 1 times 8, 1 times 12, 1 times 16. There's that value right there. That's 16 kip feet of moment. And when you turn the corner, that's 1 times 16, that's 1 times 16, that's 1 times 16, that's 1 times 16, and therefore it stays 16 kip feet, and it's plotted on the tension side. That is the moment, due to the unit loads, where a unit load has been applied to the structure in the number 2 direction. If you would like to find the deflection on the real structure, what did I call that thing? Delta is due to the real loads on the primary structure. In the number 2 direction, due to the real loads, you would find it by integrating the real moment diagram, M sub P, 0, is that what we call that guy? Yeah, that's what we call that guy, times the moment due to the unit load in the number 2 direction, dx over EI. In other words, you would volume integral this guy, these guys, with these guys. And that would give you delta 2, 0. If you are home, your television is broken, your dog has died, so you're looking at these equations. It's the only thing I can imagine that you would be looking at these equations, and you want this guy right here, delta 2, 1, you would go looking for the unit load applied in the number 2 direction, and you would combine it with the moment diagram M sub Q1. So delta 2, 1 is equal to the integral of M sub Q2 M sub Q1 dx over EI. And lo and behold, you would be this much further towards your goal. You would know that number.
You just integrate for 1.
You integrate over the entire lengths. In other words, you'd integrate this triangle, you'd integrate this nothing with this something and get nothing. You'd integrate this triangle with this rectangle, and you'd get LAC over 2. And you'd integrate this triangle with this nothing, and you'd get nothing. You add up everything in sight. In other words, you'd add this volume integral with this volume integral with this volume integral, and you would have delta 2, 1. And you would then fill it into this slot right here in your equation in MATLAB. And you still have quite a few to go. Incidentally, you do not now have to do this one, delta 1, 2. And the reason you don't have to do delta 1, 2 is why? Because it's the same as delta 2, 1. That's correct. And let me prove to you that delta, I'll be doing this all day long. Let me prove to you that delta 1, 2 is the same as delta 2, 1. QED. Don't remember what that stands for. It's quantum estratos demonstratum or something, I don't know. But it means, there it is. Whereas a minute ago you combine this multiplied times that, now you combine this multiplied times that. Same pictures. They're just in reverse order, you get the same answer. And so on down the line. There are your moment diagrams due to a unit load in the number 3 direction. That's a concentrated moment. Answer is 1, 1, 1, 1, 1, 1, 1, 1, 1, all the way down. That's a 1, that's a 1, and that's a 1. And if you want to get delta sub 3, 1, you would combine this one with the moment diagram that we had for the number 2 unit load. And here are all the rest of them. Here's the moments with a unit load in the number 4 direction. Looks just like the previous one. The only thing is it doesn't start out here on the top, it starts here. Here's when you have a force in the number 4 directions. Looks the same as that other one. The only thing is it's down a notch. And then for the moment 6, a 1, a 1, a 1. And then 7, 8, 9. And they start looking very familiar. Whoops, that's wrong. As you might imagine, all I did was copy these things and then adjust them to fit. What should that one look like? Very good. Should be down here like this. And it should be across here like this. And that piece, those pieces shouldn't be there. That one I happened to get right. Didn't miss that one. How about the previous one? The previous one was okay. All right. So I'm going to put the original released structure up there. Well, that's good enough. And I'm going to tell you that this is R1. And this is R2. Which way did R2 go before? Here it is. And this is R2. And this is R3. R4, R5, R6, R7, R8, and R9. And I want you to give me, this is again 16 feet, 12 feet, 12 feet, 20 feet. And there was a uniform load across the right-hand side of 4 kips per foot. The entire frame has a flexural rigidity of EI. And I want you to tell me the following number, the deflection in the number 7 direction due to the real loads. Put your name on the top of it. And I also want you to tell me delta 77. I got started a little late. When everybody has the problem copied down, I'll go ahead and throw the moment diagrams up there. Somebody stole them. Gitman?
Yeah.
Did you get my moment diagrams?
Yeah.
There's 9, there's 8, there's 6, there's 5, there's 4, there's 3, there's 1, there's 2, there it is. How could I not have the one I need? Ah, there it is. If anyone would like to lease a volume integral because there isn't one within 30 feet of you, ask everyone in the area to raise their hand, and I will let one of you from the middle of that little pocket of ignorance come get one. Has everybody got access to a volume integral chart? Oh, you must be kidding, Gitman. I wouldn't give you.
I keep it at home.
You keep it at home, yeah. It keeps your dog warm. My dog ate it. Who's got the value in the middle of this 20-foot piece so I can go ahead and put it down? I think you need the value in the middle for a parabola, don't you? For uniformly distributed loaded, yeah. Started out here. Oh. Oh, okay. No, I don't care. Change it back to 3. Sorry, I meant to use the same numbers. Thank you. Well, let's see. It can't be that hard, can it? It's 3 kips per foot times 34 feet times, where did that come from? 3 times 12. That's at the top. Times 6. That's 3 times 24 times 12. So that's times 24. So that's 3 times 34 times half of 34 is 17. So there's your moment at the ends in the middle of the moment due to the real loads, and here's your moment due to a unit load. Who's got this number for me? 20. Most certainly, because all you got a 1 here and a 1 here, and it's 20 tall. And this triangle combined with this nothing is going to give you a nothing. And all you got to do is plug in your volume integral for this parabola combined with that triangle. And you've got your answer for delta 7, 0. And delta 7, 7 is nothing but this guy on top of himself. Why is it a minus? Why is this one a minus? One's on one side, one's on the other side. Well, I didn't know it'd take this long. Hand it in next time.
Why'd you use that integral?
Oh, you want me to integrate it? I could. You know.
Why LA over 6?
Oh, why do I use that volume integral?
Yeah.
Well, I'm trying to combine a parabola with 0 with a number, a number, and a number. And it only requires 2 of them with a triangle, and that's the one that looks like LA on the 2D plus C over 6. Not this one? I'm sorry? Well, I put the 0 end on that end for no reason. I was going to make C 0, and then D is something, then E is something. I'm sorry, tell me again. Well, I was going opposite directions. I was combining them like this. I put the Z. Well, one end's not 0. As long as you put the right terms in there, I don't think it matters which one you use. A is the triangle. CDE, I said C would be 0. 2D plus E. Hand that in next time. All you need, I'll post these. All you need is the dimensions and which one I'm looking for. And if you have it, you want to throw it in, go ahead. Let me get all this stuff out of the way in case somebody hands that in.
Do you not take any lights at all?
Yeah, no, it ought to be worth half.
The syllabus says 25% off for the first day.
Does it? Well, it sure could, because that syllabus was resurrected from the dead